These are some practice questions in electric fields. Always a good idea to have a data sheet at hand. And the first question is about proton and electron separated by a distance as specified. What's the size of the force? So the force between two charges, the electrostatic force given by Coulomb's law, which is given in the data constant sheet. So we have that the force is equal to 1 over 4 pi epsilon naught Q1 Q2 over R squared, where E naught, epsilon naught is the permittivity, free space. So we're assuming this is happening in free space. We have the charges on the proton and the electron, and we have the distance between them. So just very straightforward, just need to put the numbers into the equation. One we're missing is the permittivity of free space. Again, getting this from the data constant sheet. Okay, so we have force is equal to 1 over 4 pi times so put the numbers in into the calculator, get an answer of 9.207 by 10 to the minus 8. One significant figure given the question, so I'll write it one significant figure, 9 by 10 to the power of minus 8 newtons. That's answer B. Okay, question 2 is the same arrangement of the proton and the electron, same distance apart, but now we're looking for the potential energy. So the numbers are the same as in question 1, and here we're using the electric potential equation. So we have that V is equal to 1 over 4 pi epsilon naught, and in this case Q over R. So that means the potential that distance away from one of the charges is 12 multiplied by 0.60 by 10 to the minus 19 divided by 5 by 10 to the minus 11. So that gives us an answer of 28.8 volts, and remember that's 28.8 joules per coulomb. So that's for that's the potential per unit charge, and the charge in either the proton or the electron is the elementary charge. So we can convert that to joules by multiplying by 1.6 by 10 to the minus 19, or we can write this as the potential energy is going to be 28.8 electron volts. Answer C. Okay, and question 3. An electron starts at rest and then is accelerated through a potential difference of 1200 volts. The speed, we're looking for the speed of the electron after it's accelerated through that potential difference. So for this question, we're looking at the electron losing electric potential energy and gaining kinetic energy. So what we have is we will have that the kinetic energy is going to be equal to the change in potential energy, which is going to be the elementary charge, as it's an electron, multiplied by, I should really write that as the change, the potential difference, the change in potential. Okay, so that I can rewrite that as V is equal to the square root of 2E change the potential difference divided by M. Okay, now the mass of the electron, we can get this from our data sheet. So that gives me that V is equal to the square root of 1.60 by 10 to the minus 19 multiplied by 1200 divided by 9.11 by 10 to the minus 31. And I put that into my calculator and I get an answer of 2.05 by 10 to the 7 meters seconds minus 1. It's not so as possible, less than the speed of light, so that's fine. And I check what our options are. So this means this is answer D. Okay, question 4. It says on a dry day, the electric field near the surface of the Earth is 140 volts per meter downwards. A drop of water of mass 4.2 milligrams is suspended in the electric field. What is the charge that the drop carries? Okay, so here, just a quick sketch to show us what we have. The electric field is downwards. The electric field is downwards, like so. We can assume it, well, we're told it's uniform because we're told that the electric field strength is 140 volts per meter, and we're told that the mass is equal to 4.2 by 10 to the minus 3 grams. That's equal to 4.2 by 10 to the minus 6 kilograms. And we're looking for the charge. Now what that means is, because the mass is suspended, we have the force downwards due to its weight, and we've got the electrostatic force upwards from the electric field. Okay, so we can work out the force on the object is going to be equal to the weight, which means that we have the electric field times the charge is equal to the mass times gravitational field strength, which gives us that the charge is equal to mg over E. The charge is equal to the mass kilograms multiplied by gravitational field strength. It doesn't give us a number here, so we're going to assume that get this number from the data sheet, which is gravitational field strength 9.81 newtons per meter. That's all divided by electric field strength, which is 140 volts per meter. Put that into the calculator. So that gives us the charge upwards was equal to 2.94 by 10 to the minus 7 coulombs. But we have to remember, so the direction of the arrows on the electric field, this shows us the direction of the force on a positive charge. Since the force is upwards, that means that the charge must be negative. So this is the magnitude of the charge. Therefore, it's going to be the charge is equal to minus 3 by 10 to the minus 7 coulombs, which is answer B. Question 5 can seem a little bit tricky at first. We have to decide which of the sketches represents the the electric field that varies along the line AD, where we have two equal positive charges placed at points along that line. And if I just sketch what that looks like, what we're saying is we have two positive charges like this. And let's remind ourselves, if we have a positive charge, it means that the field is radially outwards, like so. And we can remind ourselves what that would look like if we made a sketch of the electric field. So it's useful just to always have an idea to be able to sketch what the electric field looks like in the case of having at least 2 points. So this is where we have a positive charge and a negative charge. We get an electric field looking like this. The arrows are coming out from one side, going in to the negatively charged side, and here where we've got the same, both positively charged, the same size, here we have the shape of the electric field shown there, and we see that in between the charges there's a point where the electric field strength is 0. So the first thing I would do answering this question is I'd just make a really quick sketch for myself, just to remind myself what that's going to look like, which is something like this. It doesn't have to be very accurate unless they've asked you to draw the field in a question. The most important thing is to remember in this case, because it is positively charged, then the arrows will all be outwards. Okay, so this is what the situation is we're talking about. Question 5, this is what my sketch of the electric field looks like. Okay, and what we're saying is we're coming along this point here, and we're trying to identify what would the electric field strength look like along that line. Now the point is that the electric field is going to get stronger as we approach the charges from either side. So we're going to have a very large electric field here. But in this case, remember, the electric field represents the force per coulomb. The force is acting this way in the case of this charge as we come towards it, and in the case of this charge it's acting in the other way. So we have to show that on our graph. So if that's the electric field, what I would be saying is the electric field, for example, is getting stronger as we approach here, and it's getting stronger as we approach on this side, but in the opposite direction, because this one's going to put the arrows in this direction, and here the arrows are in this direction. Okay, and then we have a point in the middle where it's going to be 0, and then again it's going to be increasing as it approaches this charge, but now the arrows on this side are in this direction, so it's going to be like that, and the same on this side, like this. And that is most like answer B. For question 6, we're asked to say which graph shows the variation of the electric potential. And to do this, I used this information from my data constitute, which told me the electric field strength is equal to the gradient of the graph of the potential. So looking at my electric field strength, I'm looking at the gradient of this line. So we can see the gradient of the line here is positive and large. Same here, positive and large. Same there, and same there. So that allows me to define 4 points in my graph there, and that's actually enough for me to be able to identify which of the answers it is. We also see the gradient tends towards 0 at each of these points, so I'd expect it to look like this, which is answer A. Now in question 7, they replace the positive charge at C by a negative charge. So once again, first thing I'm going to do is I'm just going to make a quick sketch of my dipole, just to remind myself what the situation that I'm dealing with, which of course look like this. So now I'm going from this type of diagram to this type of diagram. I'll just make a sketch of that so that I've got an idea of what I'm doing. So again, pretty rough sketch, but it just allows me to get my mind around what's happening. And again, I have to determine what is the variation of the electric field along the line. So I'm interested in these points here. So again, the electric field is going to be very strong on this side, wherever as I'm approaching this this charge, and the force is in that direction. And same here, it's going to get strong, but the force is still in this direction. So now I expect this side to look like this, because it's in the same direction as this one. And then on the other side, it's getting stronger as I approach here, but now it's in the opposite direction, and the same on that side. Okay, because the direction here is the same as the direction here. Okay, so this is the sketch that I've made of my graph, which looks most like answer C. And then question 8. So question 8, I'm going to do the same thing that I did before, using my knowledge that the electric field is equal to the gradient. But unfortunate that I've done it on the succeeding page. What I'll do actually is I'll do it on the page here, that way we can keep it together. So question 8, I'm using this idea, and so now I can make a sketch of what this is going to look like. Looking at the gradient, it's large and positive, but this is large and positive here. This one is large and negative, and this one is large and negative here. Once again, low gradient here and here and here, so I'm going to get something that looks like that, and then like this in the middle, and the one that looks most like that is answer D. And then we've got question 9. We've got, it shows us a series of equipotentials, and we have to work out what the statement is not true. So these are the equipotentials that it's showing us. Okay, and it says the work done in taking a charge from 0.1 coulombs from A to B is 0. So A to B, A and B are on the same equipotential line, so that means there is no work being done moving from A to B, so that means that A is correct. Then we have the work done taking a charge from A to C is 4 joules, so the difference in potential is equal to 80 minus 40 equals 40 volts. We've gone from A to C, we've gone from 40 volts to 80 volts. And to work out the change in energy on the work done, again we just use the equation sheet. We've got work done is equal to Q times the potential difference. So I'm going to move on to the D option, which is the direction of the electric field is downwards. And in the equation sheet, it gives you the field strength is equal to the gradient of the potential, but we have to remember the direction. Okay, so in fact, the electric field strength is equal to minus the gradient of the potential. So as the potential is increasing in this direction, it means that the electric field strength is downwards. So D is correct. Now for C, it says the electric field strength at D is stronger than the electric field strength at B. Easiest way to look at this is looking at the equipotential lines. The equipotential lines are drawn like this, and all we have to do is remember that I can make a sketch of the electric field, but remember the electric field lines are at 90 degrees, which means electric field lines are like this at 90 degrees. This is a uniform field, which means the electric field strength doesn't change. So C. So question 10, we're told what the electric field is a particular distance away from the surface of a charged sphere. In this case, 10 centimeters away from the surface of radius 20, so that's 30 centimeters away from the center. What is the electric field strength at distance 70 centimeters away from the surface? So I just made a quick sketch for myself. So the electric field strength at point A is 900 newtons per coulomb at that distance. What is the electric field strength if we increase the distance to 0.9? So the electric field strength given by the equation from the data sheets. And it means that we can say the electric field strength is proportional to 1 over R squared, because everything else will stay the same. So I can write that as E is equal to K over r squared. So the electric field strength at A is k over the distance to A squared, and the electric field strength at point B is k over the distance to point B squared. So I can get the ratio of the electric field strength at B compared to the electric field strength at A is r A squared over r B squared to give me this equation. So I can now just substitute in to that, which gives me, I've got 0.30 squared divided by 0.90 squared multiplied by 900 newtons coulombs to the -1, and put that into my